Hello students, my name is Shashank Shekhar. So we were going with the alkene. We have seen the isomerism part. Also we have seen the nomenclature and all. Today our focus will be on preparation mainly and on reactivity. So two things will be the main focus of this lecture. So let us start our lecture. So first of all, we will look at the preparation of alkene. What are the methods of preparations that are used for the preparation of alkene? Second thing, that something attracts us more, because why it is attracting us more, because students do often prepare for the reactions and all, but they don't go for the physical properties. Sometimes in the question, in the CBSE exams questions, what is done, that your OR type questions are asked, in which the in the OR part we have the physical property, means a question related to physical property. And believe me, physical properties are much more easier to explain in comparison to the chemical reaction or preparation, because see, it is very difficult to sometimes predict the product. Okay, even if you have learned whole of the reactions and all, but sometimes it become difficult. But physical properties cannot vary much. You have 2 to 3 physical properties, and all of those questions revolve around those properties, and there are 2 to 3 exceptions which you will cover. Okay, so I would suggest you that just don't let go of these physical properties. Grab it, have, and try to just cultivate this opportunity, right? Okay, at last we will see the chemical properties. Now, first preparation will involve the preparation from alkyne. So so we till now we have not moved up to alkyne, although you know that the alkyne means the one which are having carbon carbon triple bond. So what we do is that we do the partial reduction, okay, with partial reduction of this alkyne. Why don't we do the full reduction or the complete reduction? So when there is a complete reduction, it converts your alkyne to alkane. Okay, converts your alkyne to alkane means it does not stop at double bond, it goes to the single bond. So that is the reason we do the partial reduction to go up till the double bond. And for that we take a calculated amount of dihydrogen. Okay, we take a calculated amount of dihydrogen, and then in the presence of pelletized charcoal, which is partially deactivated and with poison sulfur compound. So what is the meaning of poison here? So catalyst is something which enhances the rate of reaction. We know it very well, and it always enhances the rate of reaction no matter which reaction we are talking about. And for those substances which kind of reduce the rate of reaction or hamper the rate of reaction, those are considered to be as inhibitor or poisons. So here we have taken such one such compound, which is a sulfur compound, or it can be quinoline, that will hamper the rate of reaction, or the say, you can say that the reactivity of the hydrogen. Okay. Now, this partially deactivated pelletized charcoal is also known as Lindlar's catalyst. So this is a very, very, very important for catalyst for you. It is called as Lindlar catalyst. And the second most important part of this reaction is that this reaction often gives us cis geometry. So it will give you cis geometry. However, alkyne on reduction with sodium in liquid ammonia form transalkene. So I would say that this line is very important for this whole chapter. So I would put this on the second or third priority in terms of importance, right? That if you are doing the reduction of alkyne, and if you are doing it with the Lindlar's catalyst, that is the partially deactivated pelletized charcoal, then it will give you cis geometry. And if you are doing it with the sodium in liquid ammonia, then it will give you the trans geometry of the alkene. Clear? Okay. So this is the thing that I want to focus on. Now, next, here is the reaction. You have your reaction here. So here is your alkyne. Okay, here's the alkyne. So when we are doing it in presence of palladium and charcoal, we are adding the hydrogen. Then this alkyne is getting converted to cis alkene. Now, why it is happening? so in this type of addition, in which you can see that both of the hydrogen are being added on the same side. Okay, you can see that this hydrogen and this hydrogen are on the same side. So this type of addition are called syn addition, right? This type of addition are called syn addition, and it is because of the mechanism it gives such reaction. So basically we are having a palladium surface on which the reaction is occurring. So the alkyne, that is the substrate, and your hydrogen, okay, which is being absorbed on the metal, they are on the same surface. So it comes like this, okay, it comes like this, and both hydrogens are present here, okay, two activated hydrogens are present here that are being absorbed earlier, and now a alkyne comes and the lone pair of alkynes interact with these two hydrogens, and that results in syn addition, okay. So means it is added on the same side. Now in comparison to that, if I talk about the reduction that is accompanied by the sodium liquid ammonia, this has a different mechanism, and it is, of course, it is an anti-addition. So it is called as syn addition, and this is called as anti-addition. So in anti-addition, what happens? That sodium is a metal. We know that very well. Okay, sodium is a metal, right? Now sodium is a metal, so it can donate electron. So it donates electron on the one side, and on donation of electron, this pi bond breaks and a negative anion is formed on the either side. Clear? So it creates a cross type of geometry. So if electron is added on this side, the lone pair will go, the bonded pair will go here and form a negative charge on the cross side. Now this negative charge takes up the hydrogen. Now sodium gives another electron, and this radical that is been created. So initially a radical would be created because one electron is being donated. This radical gets one more electron and it gets another hydrogen, and therefore since there is a formation of anti across type of structure, right? So because donation is on one side and creation of anion is on other side, so this gives us trans alkene. Okay, this gives us trans alkene. So this is very, very important reaction. So you can see that since this hydrogen are present on the either side, so they are trans alkene. Again, we have taken a specific example here. So these are just what? These are just general example. We have taken a specific example in which we have ethyne. Now here we have no matter of the syn side trans because both of the substituent are initially hydrogen and we are adding hydrogen only. So a carbon would contain two hydrogen, and that would not create any what? That would not create any trans or cis. Okay, because all the substituents are same, and specifically on each carbon both substituents are same. And we know that if the doubly bonded carbon, if suppose two carbon are doubly bonded, and if in either of them, okay, if any of them has the same substituent, two same substituent, then it cannot show cis trans isomerism. The another example, if we talk about the other example, here also it cannot form cis and trans because this carbon, okay, this carbon has two same hydrogens, okay, so we cannot have cis or trans. Clear? Okay, so this is an important reaction. Now we are done with the preparation from alkyne, which we have basically focused upon, the reduction part. Now the second one is alkyl halide. So this is also very important. So what we do, say we take a alkyl halide and we treat it with potassium hydroxide in alcohol. In this we called it as alcoholic KOH. Okay, so we term it as alcoholic KOH. And what happens in this case? In this case, one molecule of halogen acid react to form alkene. Okay, this react to form alkene. So this reaction condition is very important, that it should be mentioned that potassium hydroxide is added or it is reacting with the substance with the substrate in the presence of alcohol. So alcohol presence is very important, or it will not give you the elimination product. So this is simple elimination of the OH group, so it is called as elimination reaction. Or if you want to talk it in a more specific way, then it is called as dehydrohalogenation, because in this reaction one halogen and one hydrogen both are lost. Okay, and one hydrogen and one halogen will form halogen acid. Okay, so removal of halogen acid, you can also say it as removal of halogen acid or dehydrohalogenation. Now this is an example of beta elimination, since hydrogen is eliminated from the beta carbon. So what I'm saying here is that, so here, so if you take this structure, right, now this is the carbon that is holding the halide group, so the halogen group, and this is the carbon that is beta with respect to this carbon. Okay, Now we can have this beta carbon on the either side also, but here we are having only 2 carbons. So this is called as beta carbon. And since the base will abstract proton from here, okay, it will abstract proton from this hydrogen, and this bond pair will move here, and this X will be kicked out. Clear? So this is the reaction, and since the elimination is taking at the beta position, so it is called as beta elimination. So see, the reaction condition is written like this: alcoholic KOH. This means AlCKOH means alcoholic KOH, and that also in the presence of heat. Clear? So this reaction is also very, very important. This all reactions are very important. Now here X can be chlorine, bromine and iodine. It cannot be fluorine. So this should be also kept in your mind. Next is, it is seen that iodine reacts faster, means alkyl halide containing iodine reacts faster, then comes bromine, and at last comes chlorine. What is the reason behind it? The reason behind it is that the carbon iodine bond is weaker as compared to carbon bromine bond, because iodine is larger in size, so the bond length has increased, and hence the bond enthalpy is weak. Okay, so it is a weaker bond. Now this is in a reference with your halogen. Now if you are talking about the alkyl group, then the tert-butyl group is the one which is reacting faster. Okay, then we have secondary, and then we have primary. Now whenever you see this kind of trend in reactivity, the tertiary, secondary and primary, then there is a question that why it is happening so. So for that we have to wait for some time. So when we will study the syllabus of class 12, you will understand that why it is happening in this fashion. But now, for now, just keep in your mind that when you are doing the beta elimination, then tertiary will react faster, then comes the secondary, and at last we have primary alkyl group. Clear? Okay. Next is from vicinal halide. So first, what is the meaning of vicinal halide? So there are two kinds of dihalides. One is vicinal dihalide, second is geminal dihalide. If both of the halogen group are present on the same carbon, then we call it as geminal dihalide. And in this case, both of the halogen group are present on different carbon, but they are on the adjacent carbon. So these are called as what? Those are called as vicinal dihalide. So this is important. Okay, so this is important that the halogen should be on two different group as on two different carbon, and those two carbons should be adjacent to each other, means next to each other. Then only we can call it vicinal dihalide. So in this reaction, with what we do, we treat with vicinal dihalide with zinc, and this reduces our vicinal dihalide to alkene. Okay, and this is called as dehalogenation, because we are removing both halogens, so it is called dehalogenation. The previous one was called dehydrohalogenation. Again, we have another example here. We have taken another example, and also this also results in the alkene. Clear? Okay. Now the side product is what? ZnX2, where X is the halogen that is being present as the vicinal halide. Clear? Okay. So next is from alcohol by acidic dehydration. Okay, dehydration means what? To dehydrate something. So you must have heard this word, that dehydration means that you are removing water, you are dehydrating it. So what we do, we take alcohol and we dehydrate it, means we remove H2O from that, and that results in the formation of alkene. So if you don't remember, then alcohol is what? Alcohol is the hydroxy derivative of alkene. So what we do, we take a hydrogen. Okay, we take a hydrogen, we remove that hydrogen, and we place a hydroxy group, that is a OH group, instead of that, say, your hydrogen, right? And that is called as alcohol. So we know that. Okay, so I'm just saying it so that you can get an idea about what is alcohol, because sometimes things slip from our mind. Okay, now here is a solution. So here is a reaction. So what we are doing here is we are treating your alcohol in the presence of conc H2SO4 and heat. So you will see that this reaction, we are seeing it very often. It is called as elimination reaction. We are eliminating a group, and we eliminate it in the presence of heat. Means elimination reaction is favorable at higher temperature. We can say that now, because elimination reaction is taking place at higher temperature. Now since a water molecule is eliminated from the alcohol, the reaction is known as acid dehydration of water. Okay, so this is called as acid dehydration of water. Again, You should keep the reaction conditions in your mind, that this is also a beta elimination because the hydrogen is being removed from the beta carbon. And what we are doing is we are treating alcohol with the conc H2SO4 in the presence of heat, and this on beta elimination is giving us an alkene. Clear? Okay. Now, what may be the probable path that this reaction would have taken? So I am just giving you a hint here. So since we are doing it in the acidic condition, so this oxygen as a lone pair, this will accept one hydrogen and create H2O plus. Now this H2O plus will leave by itself because it is a good leaving group, and now the hydrogen will be taken by the base, and this bonded pair will move here and make double bond. Okay, so this just a go through for you, so that if you are saying that how this reaction is going, then you can think it in this way, right? Okay, so this is the again the beta elimination to form the alkene. Now we are done with the preparation method. So if I just get back and get a quick revision of what we have studied. So we have done it from alkyne. So what we have done reduction, two type of reduction. One is from palladium and charcoal, which gives us cis, and another is from liquid ammonia and liquid NH3 and ammonia sodium, which gives us what? Transalkene. Now this palladium charcoal is also called as Linder's catalyst. Next we have seen it from alkyl halide, where we have done the beta elimination in the presence of alcoholic KOH, and it is good to do the reaction with iodine, then with bromine and fluorine does not give this reaction. If you take the alkyl group, then tertiary is the most reactive one, then the secondary, and then the primary. The third one is from the vinyl dihalide, which is this reaction is called dehydrohalogenation, while this one is called dehalogenation because we have a vinyl dihalide, means both two halogen groups are present, and they are present on the adjacent carbon, and upon the reaction with zinc, it is giving us alkene. Okay, plus ZnX2, where X is the halogen that we are taking. Now we can do another reaction, another preparatory method, that is from alcohol. So we are again doing the beta elimination, in which we are taking a alcohol and treating it with H2SO4 and heat. That gives us a beta eliminated product, which is again a alkene. Now physical properties. Now coming back to the physical properties. So what are physical properties? So alkene as a class resembles alkanes in the physical properties. So they are similar to alkanes in the sense of physical properties, except in the type of isomerism and difference in polar nature. Okay, so there is some sort of polarity in case of alkene due to the double bond, but that does not affect the physical properties more significantly. And the isomerism is different. They can show cis-trans isomerism apart from the structural isomerism like the chain and position, and that is the addition point for the alkene. If I talk about the physical state, then the first three members are gases, the next 14 are liquids, and the higher ones are solids. Again, I am making a very short point here that alkenes are also called as olefins. So this is an important part. Maybe question may not be asked directly that what is the other name of alkene, but olefin word may be used, and that may confuse you. Okay, ethane is a colorless gas with a faint sweet smell. The other alkenes are colorless. So if you talk about the aroma, okay, or the order, I would say, if you talk about the order, then ethene is a colorless gas and a faint smell, whereas the other alkenes are colorless and odorless both. They are insoluble in water but fairly soluble in polar solvent like benzene, and this is obvious because they are very non-polar in nature. Okay, they are non-polar in nature. Now they show a regular increase in boiling point with increase in size. So this is very, very important point, that if you are increasing the size of the molecule, or if you are increasing the molecular mass of the molecule, then you are increasing the van der Waals force. Okay, so this is a very, very, very important point. Okay, now we have talked about three things: the physical state. So first three members are gases, other are liquids, and after 14 we have solid. Okay, ethane is a colorless and odorless gas. Sorry, it had a sweet smell, but it is a colorless gas. Whereas the other alkenes are colorless and odorless. If we talk about the solubility, they are soluble in pure non-polar solvent, whereas insoluble in water, and they show a regular increase in the boiling point with increase in size. So what is the reason behind this? Why is the boiling point increasing with increase in size? So let us see to that. Okay, now alkenes are a rich source of, so yeah, coming back to here. So why is this boiling point higher? So the reason is the van der Waals force. Okay, where the van der Waals force is the main factor deciding the boiling point and all, because there is no polarity, so there is no dipole-dipole interaction. So the only factor that is contributing to the boiling point and all, so that is our van der Waals force. So as the size increases, the van der Waals force increases. Now a very important point: if you have several alkenes with you that has the same molecular mass, then you will look upon branching. The one with a greater extent of branching will have a lower boiling point, and one which have less branching will have a higher boiling point. Now coming to the chemical properties. Okay, coming to the chemical properties. So since alkenes held pi electrons, so they have pi electrons, we know it. Okay, and these pi electron are very susceptible to reaction because pi bonds are weak in nature, so these electrons can be easily donated, and that is the reason they show addition reaction. Okay, they show addition reaction, and due to the addition reaction, so the addition reaction, we have talked about addition reaction when we are talking about alkyne. We have seen the addition of the hydrogen, so similar to that we can also add hydrogen to the alkene also. Okay, and some reagents also add by free radical. Okay, some are added by free radical, and some are added by transition state, and the others are added by the ionic or ionic state, right? Now these are cases where under special condition alkenes go free radical substitution reaction. Now if I talk about some reactions, so we have reactions like oxidation and ozonolysis. So these are the quite prominent, means significant reaction in alkene, so we'll talk about it. So this is very, very important, and I would say primarily ozonolysis. Okay, so this is of more significance. So some important reaction if I want to mention, then that would be the alcoholic KOH reaction. Okay, now I will talk about the more primer one. So Lindlar catalyst and your palladium charcoal difference should be in your mind, and this second thing is your ozonolysis. Okay, this is also very, very important. So first of all, addition of dihydrogen. So similar to your alkene can also add up one dihydrogen gas in the presence of finely divided nickel, palladium, platinum. So in this case we don't use any poison like sulfur gas, sulfur molecules and all, so that results in the reduction of alkene to alkane. Second is addition of halogen. So if you add a halogen to that, then so halogen means halogen like bromine and chlorine add up to alkene to form vicinal dihalide. Means both, if you are adding Br2, then it will be added across the double bond. Both bromine will be added across the double bond. Iodine does not show addition reaction under normal conditions. So this is very important point, that chlorine and bromine show addition reaction, fluorine does not show. Okay, chlorine and bromine shows. Iodine also shows addition reaction, but that is not under normal condition. Okay, so these are the reactions that we have. So what are we doing? We are taking CCl4 and adding, using it as a solvent, and we are adding this Br2 molecule to this ethene, that results in 1,2-dibromoethane, right? Now the reddish color of bromine solution. So bromine, this is very important reaction, decolorization of bromine water. So if you take bromine water, it is orange in color. Okay, but when you treat it with alkene, the orange color of the bromine fades away. Okay, or it become lighter due to the removal of Br2. And why it is removed? Because it is being added to this alkene. Now this is used as a test for unsaturation. So if you have a double bond in your compound, then your bromine water will be decolorized, and this is a very important reaction. Questions are often asked, and you must have heard this term to and fro, decolorization of bromine water. So if there is unsaturation in your compound, then it will decolorize your what? It will decolorize your bromine water. Okay, clear? Next is addition of halogen to alkene is also an important example of addition reaction involving cyclic halonium ion. Okay, so it forms a cyclic halonium ion. Okay, so we will not talk about the cyclic halonium ion, only we will know that okay, there is something halonium ion is formed which is involving a cyclic transition state, and it gives us this reaction. Now talking about the hydrogen halides, so we have already said that hydrogen halides are being added. So if you talk about the order of reactivity, then the Hi is added fastest, then comes the HBr, and then comes the HCl, right? Also, like addition of halogen to alkenes, addition of hydrogen halides is also an example of electrophilic addition. So this term is very important, which is electrophilic addition of reaction. Okay, electrophilic addition reaction. So like addition of halogen to alkene, it is also added, and the order of reactivity should also be remembered that halide HI reacts faster, then comes the HBr, and then comes the HCl. So this is an example for you. So if you see here, there are two possibilities of addition. In case of symmetrical alkene, we don't have to worry. Okay, if Br goes here or H goes here, or Br goes here, H goes here, we'll give you the same reaction. But what about the unsymmetrical alkene? Okay, so this is symmetrical alkene, we don't have to worry. So it gives us your normal electrophilic addition mechanism. Now coming to unsymmetrical alkene, so this is your unsymmetrical alkene. Two products are possible. So this is very important. It will be used in your later on classes, in your later exams, any exam you give, you will face this Markovnikov rule. Okay, you can't escape from this Markovnikov rule, and this is very easy to understand also. There is nothing complex in this rule. Now, talking about the Markovnikov rule, so what we do is we take a alkene, right? Which we take a alkene which is unsymmetrical in nature, and we add HBr. Now H can go on this carbon and Br can go on this carbon, which will give us this product. Now H can go on this carbon and Br can go on this carbon, and that will give us this product. Okay, these are the two possibilities. Now if you talk about HBr, then Br is the negative part because it is more electronegative, and H is the positive part. Means there are two possibilities. Again, we can say it in this way also, that the negative addendum can go to the terminal carbon, or the carbon which is not attached to any other carbon, and it can go to the other carbon, right? Now according to this Markovnikov rule, bromine always goes to that carbon, or the major product is that alkyl halide which has the greatest number of, which has the lowest number of hydrogen attached to bromine. Okay, or I would say, so since if we are talking about this double bond, if we remove one bond from here, suppose, then this will create what will do, it will create carbocation. Okay, so out of these two carbons, whichever forms the more stable carbocation will get the bromine, and that is called as Markovnikov rule. Clear? So this is very, very important. This Markovnikov rule is very, very important. If you are doing with the CBSE exam and all, you don't have to worry much about the stability of carbocation. You just have to see that out of the two doubly bonded carbon, which is having the least number of hydrogen, and the bromine will go to that. Simple as that. But in actual principle, if you talk about, then it involves the stability of carbocation. It should deal with the stability of carbocation, and then we can add it. Okay, clear? Now this is called as Markovnikov rule. Now sometimes we need a reaction or we need a product that is inverse of that. There are possibilities because multiple compounds has multiple uses. So if you have to add Br opposite to the part where it is going, you have to add something called benzoyl peroxide. Okay, this is called as benzoyl peroxide, and in this case the addition is anti-Markovnikov type. Okay, anti-Markovnikov means the negative part of that, means the negative addendum will go to that carbon which has least number of hydrogen, which has greatest number of hydrogen. So these are the two carbons. Okay, so we have added what? We have added here benzoyl peroxide. Now the Br will go to this carbon and not this carbon, right? Clear? So this is very, very important, and this is called as what? This is called as anti-Markovnikov rule or peroxide effect, because it is happening due to the presence of peroxide, or it is also called as Kharash effect. Now a very important point for you, that it cannot happen with HCl or HI. So sorry for that. So I am saying that it can only be, this means this Kharash effect can only be seen if you are using HBr and not HCl or HI. Clear? Okay, so this should be always in your mind. So this is a very, very important part here, that you should remember, that if you are saying that, okay, we have used the Kharash effect on say HI or HCl, then that would be completely wrong. So it should be always in your mind that only HBr can do it. So now for that, why can HBr do so? Why can't this chlorine or iodine? So for that, you have to look at the mechanism. So here is a mechanism for you. So this goes through a free radical mechanism. So first we have the benzoyl peroxide. Okay, we know that this is the benzoyl peroxide. Here is a peroxide bond, and the reason behind this formation of radical is that this oxygen single bond is very weak. Okay, this peroxide bond is very weak, and when we treat it with heat or something like that, then it gets homolytically cleaved. So one electron goes here, other electron goes on this oxygen. So this will create 2 moles of this radical, and this will further decompose. Okay, this will further decompose, and when it will release 2 moles of CO2 and 2 moles of phenyl radical. Okay, is this first step clear to you? So we have benzoyl peroxide that first gets homolytically cleaved to form this, and further this CO2 is released, forming a phenyl radical and 2 moles of carbon dioxide. Okay. Now in the next step, what happens? In the next step, this phenyl radical that is present here, it takes up the hydrogen and forms your C6H6 plus Br radical. Now we have a radical here. Okay, now we have a radical here. Now let's see what happens. Now when we have radical, now this radical will take one hydrogen. It can take it from here or it can take it from here. So 2 radicals are possible here and here. Now since it is a secondary radical, so it will be more stable due to the hyperconjugation. Okay, and plus since it is electron deficient, so it will require more electron. So this will be provided by the inductive effect. Okay, so this will be more stable radical. So remember this, the tertiary radical is the most stable one, then comes the secondary, and then comes the primary. Okay, so this creates your secondary radical, and to this radical, what happens? Your H comes and gets attached. Okay, this H comes and gets attached. Now if you see here, then the Br radical is being added to this part. Okay, to this part, which is the carbon that is holding a greater number of hydrogen. Why? Because the radical that is being formed is taking up the hydrogen and not your bromine. Whereas in the case of Markovnikov rule, what will happen? The positive charge will be the one breaking the negative, taking the bromine. Okay, now again I am repeating it one more time that this cannot be done with the help of HCl and HI. We cannot do it with the HCl and HI. It can only be done if we are taking HBr. Now, what will be the reason behind it? So the reason behind it, that we have to cleave this bond in the presence of heat. Okay, in the presence of a radical. Now this is dependent upon the bond enthalpy. Since HCl bond is stronger, that is, it requires 430.5 kilojoule mole of energy. So HBr is cleaved easily, right? And whereas the HI bond is weaker, and iodine free radical combine to form iodine molecule. So see, so if you will say that okay, HBr bond is weaker, so HI bond is even weaker than that, then why it is not giving the reaction? Because as soon as this I radical is formed, it quickly reacts with another I radical to form I2. So that is the reason we don't see the reaction with HI. Okay, so these are the 2 reasons. You should remember that HCl is having a higher bond enthalpy, so it is not broken homolytically, and HI, since it is having I radical unstable I radical, so this unstable I radical quickly reacts with another I radical to form I2. Okay, that is the reason we are doing it with the HBr. Okay, so this is the minor product that we have. This is the Markovnikov product, and it is in case of Karash in case of benzoyl peroxide, this is the minor product. Okay, now next is addition of sulfuric acid. So this is very simple. So again, it has 2 parts, positive part and negative part. The positive part is going to the where? It's going where? It is going to the less carbon containing greater number of hydrogen, and the negative part is going to that carbon which is having the smaller number of hydrogen. It means it is adding in accordance with the Markovnikov rule. See, so this is the negative part. Okay, this is the negative part. So since it is symmetrical, we don't have to worry for this one. So suppose if it are not symmetrical, then the negative part would have gone to that carbon which has fewer number of hydrogen, and in this case the negative part is this. Okay, OSO2OH. So this is the negative part, whereas the H, so if you take this H out here, so this will get H plus and this will get negative charge. Okay, next is addition of water. So again, addition of water is also in accordance with the Markovnikov rule. You can see here that H2O has 2 part, OH and H. So OH is going where? The one which is having lesser number of hydrogen. So this carbon is having lesser number of hydrogen, so OH is going here, where the H is going here. Again, this is in accordance with the Markovnikov rule. Next one, oxidation. So we have done with the addition reaction. Now we will move to oxidation. So for oxidation, what we do? We take cold dilute aqueous solution of potassium permanganate, which is called as Beer reagent. these names are very important. Believe me, when you will see this in the exam, this will create confusion for you. So remember this name, Rindlas catalyst, Pierre reagent. So remember this name, it will create confusion. So when you do the reaction with KMnO4, it provides vicinal glycol. This is a very important reaction. You will get this reaction not in the linear chain, but in the case of cyclic chain also. So if you have a cyclohexene, for example, which has one double bond, then that double bond will be cleaved and one OH will be, two OH will be added on either carbon. And again, this is a decolorization reaction because KMnO4 has purple color, is a purple color solution, and whenever it is added with alkene, they decolorize the KMnO4 solution, and similar goes for the decolorization of bromine, in which the orange color of the bromine is being converted to colorless. Okay. So in this, what happens? Two OH molecule is added to the two carbons across the double bond. See, next, acidic potassium permanganate or acidic potassium dichromate oxidizes alkene to ketone. So it was simple KMnO4, cold dilute aqueous solution of Kl4. When you take the acidic form of that same KMnO4, what happens? Oxidation takes place, and the secondary carbon, means this one, is oxidized to CO, and the other carbon is also, means this bond is cleaved in between. This gets cleaved, and each of this gets oxidized. Okay, each of this gets oxidized. So since it is a secondary carbon, so it cannot be oxidized further, so it comes up to ketone only, but the other one has the possibility of conversion to CO2, so it gets converted to CO2. So this is very important reaction, I would say, because when you see this reaction in the 12th class, suddenly you say that, okay, these are not in the syllabus, but you have already learnt it all. Okay, learnt it all in this 11th class. Similarly, if you use butene, so since it is a primary alkene, so it will be converted into carboxylic acid. So 2 moles of carboxylic acid are given by this reaction. Okay, so what does acidic potassium permanganate does? It converts your alkene directly into carboxylic acid if it is a secondary one. If it is a primary one, sorry, if it is a tertiary one, then it is converted. If it is a secondary primary one, then it is converted to carboxylic acid. If it is secondary one, it is converted to ketone. Next is a very important reaction called as ozonolysis reaction, and it goes through this mechanism. Okay, so what happens in this reaction? First of all, so what do? We take our alkene, we treat it with ozone, which is O3, which gives us this propene ozonoid. Okay, and this propene ozonoid, what happens in the next step? This propene ozonoid in the presence of ZnH2O is giving us alcohol. Sorry, it's aldehyde. Okay, now how is the cleavage going? So this bond will be cleaved, double bond will be cleaved, and double bond O will be added on each of these carbon in the place of double bond. Okay, in the place of carbon double bond, each of this carbon will go at a carbon double bond O. Okay, and that is happening in the presence of zinc plus H2O. So first we treat it with O3, and then we do it with the H2O. Now this reagent is very important. Maybe this is called as workup. This is called as workup. Now this can be oxidative or reductive. If this is a reductive, if there would be a reductive workup, then you have gotten alcohol in place of this say aldehyde. And if you are doing the oxidative workup, then you may get the carboxylic acid. Clear? Okay. So next reaction is polymerization. So this is also important. This is also important reaction. So what we do is we take a ethene and treat it with take the number of n numbers of ethene, and at high temperature in the presence of catalyst, this ethene is converted to polyethene, which is a long chain of ethene molecule attached together. Similarly, we can do it with propane also. So if we treat this with a catalyst at high temperature and pressure, then it undergoes polymerization to give polypropene. Okay, so these are two important reactions of polymerization. Okay, so this was for today's lecture. With this, I end my lecture. Thank you.